Hello, welcome everyone. Let's do some questions on image processing and computer vision. First question, state two current applications each of image processing and computer vision. We know that in image processing, the input is an image, the output is also an image. Therefore, the applications are enhancing photos, visualizing high dynamic range images in medical image processing, denoising images, contrast enhancing images, and so on. Computer vision, in contrast, usually produces a decision looking at a video or an image. So, therefore, self-driving, person identification, person re-identification, object detection, factory automation are all applications of computer vision. Part B, Figure 1b shows an intensity transfer function and an input image. Apply this transfer function to the input image and show the resulting values in the grid shown. Suggest the use of this operation. So here you can see the input pixel value is shown and the output pixel value is shown. So this line is actually the transfer function. So what this means is if you input a pixel value like 100, we question from this transform what must be the output value which would result in 150. So therefore we take these values like 10 for example and see what is the resulting value. 10 actually results in 10 itself because the line is of slope 1. So 10 here, if you take 50, you can see the darkened dot is over there. So therefore the output value is 100. So 100 over here. Now if you take 120 somewhere here, you can see the value is 170. 170. So for 100 it is 150. So 150, 150. Then if you take 140, you can see it's close to 190. Then if you take 150, you can see the value is 200 over here. For 200, the value turns out to be 200 itself. And then for 220, the value turns out to be 220. Suggest the use of this operation. So you can see in this operation, the pixel values from 50 to 150 have been increased in the intensity. So this can be used to highlight pixels with the intensity range from 50 to 150. Let's do part C. Consider the gamma correction designated by G equals f to the power of gamma. G is the output pixel value, f is the input pixel value. We have to note that f and g for this operation must be within the interval from 0 to 1, and gamma has been given as 3. Q1C shows this transfer function, an input image, and a grid for showing the output. What is the effect of this transformation? So when you look at this graph, we can see that a narrow range of bright pixels. So toward the right hand side, these are bright pixels. You can see from 0.6 to 0.6 to 1, for example, is mapped to a wider range of actually bright pixels. So these are not actually bright pixels, but you can see the effect is that, right? So if you take a narrow region of bright pixels, you can see that gets mapped to a wider range of bright pixels. Okay. So this is the answer for that question. Show the gamma corrected output in the grid shown. So let's do the gamma correction for this. So let's take, for example, 200. So you can see our input value is 200. So to convert that to be within the interval from 0 to 1, we have to divide 200 by 255, and then to find G, we know that it is f to the power of gamma. So therefore G is equal to 200 divided by 255 to the power of 3, because gamma is 3. So we can do this calculation. Two hundred divided by 255, that's 0.784. We must raise that to the power of 3. It's 4.482, and that we have to multiply by 255 to convert back to that range. So the answer is 123. So 1, 2, 3. So y, the output value, is actually equal to 200 divided by 255 raised to the power of 3 times 255. If you do this calculation, you for 200 you get 123 again. For 255 you get 255 itself. Then 15 for 100, 15, 123, 1, 1, 15, 0, 0, 1. You can see that if you do a quick check, like 50, it's like 1/5 of 255, right? So 1/5, like it's somewhere here. You can see it almost maps to 0, right? Okay. Then the question on histograms. Histograms are important in characterizing images. Figure Q1D1 shows two images. Sketch the histograms of these and compare. We must sketch them and compare. So in histograms, we count how many pixels are there belonging to each intensity in the image. So you can see these are actually 3-bit images, not 8-bit images. So that's why the maximum intensity is 7. Because with 3 bits you can represent 111, which is the maximum number that you can represent, which amounts to 7. So drawing the histogram is in that case quite easy. So we have to have pixels with intensity 0, 1, 2, 3, 4, 5, 6 and 7. So we just have to count. With intensity 0 we have pixel 1, 2, just 2 pixels. With intensity 1 we have just 1 pixel over here, right? 1. With intensity 2 we have this 1, 2. With intensity 3, what have we got? 1, 2, 3. With intensity 4 we have 1, 2, 3, 4. These are coincidences. With intensity 5 we have 1, 2, 3, 4, 5. With intensity 6 we have 1, 2, 3, 4. With intensity 7 you can see there are 3. So if you add these numbers up, we must get the number of pixels in the image. That means 4 times 6, 24. Let's add 2 plus 1 plus 2, 5, 8, 12, 17, 21 plus 3 is 24. That's correct. So let's do the next histogram for the other image. 1, 2, 3, 4, 5, 6, 7. So with pixel intensity 1, there is 1, I forgot 0. With pixel intensity 1 there is 1, with 0 there are 2, with 3, 1, 2, 3, yeah, 3, with 2, 1, 2, 2, with 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 4 and 5. With 6 we have 1, 2, 3, 4. With 7 we have 1, 2, 3. Okay, computing histogram is correct. So if you add them, you get 2, 1, 2, 3, 4, 5, 4, 3. If you add them all, you get 24. You can see the histograms are identical. So the comparison is the histograms are identical for entirely different images. These images are not identical, right? Entirely different images, you can get identical histograms. Okay. The next question, figure Q1D2 shows an image and a grid. Carry out histogram equalization and show the resulting image in the grid. So to do histogram equalization, we must first get the histogram values written. So quickly do the histogram. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7. You don't have to draw the histogram here. You can just see with 7, 1, 2, 3, 4, 5. If it is correct. Now this image is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a 10 by 8 image, right? So there must be 80 pixels. With 6, 1, 2, 3, 4, 5, 6. I hope it is correct. So these numbers are wrong. 6. Yeah, let's see if there's a mistake, we will correct. 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 1, 2, looks like only 2. With intensity 3, 1, 2, 3, 4, 5. With intensity 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Intensity 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Intensity 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Tall one, 21. 21, 17, 14. So therefore histogram is correct. So these numbers unfortunately I think are not correct. I must have done a mistake somewhere. So let's erase them. Are they correct? 21, 17, 14. Yeah. So this column gets the running addition of the pixel counts. This column has the pixel count. In this one, we get the addition of pixels and multiply them by L minus 1. So L is 8 here, so L minus 1 is 7. And divide by Mn, that's the total number of pixels in the image, which is actually 80. Yes. So in the last column, we have to round it up, rounded ones, and that's actually the intensity transformation. Okay, so 21 excuse me, 17, 14, 5 to 10, 6, 5. Okay, so the sum would be 21, 38, 20 plus 1 plus 17 is 38, 38 plus 14 is 52, 57, 59, 69, 75, and 80. Now L minus 1 is 7, Nm is 80. To get this first value here, what we had to do is 7 divided by 80 times 21. Second value would be 7 divided by 80 times 38. And 7 divided by 80 times 52. Seven divided by 80 times 21, 1.837. So 1.837, and you had to round it, it becomes 2. 7 divided by 80 times 38, you've got 3.325. So when you round it, you get 3. So what does this mean? What it means is, when you have an input intensity of 0, you map it to 2. If you have an input intensity of 1, you map it to 3. So let's do exactly that. 0 means 2. So here you have 0, so you put 2 here, 2, 2, 2, and 2. There are more zeros, 2, 2, 2, 2. Okay, and for ones, we must put 3, and so on. So the rest of the values you can compute, and once these values are computed, you can fill the whole table. This is not correct. You can see this is the one that is correct, which we have copied here. Okay, thank you.